Hello, everyone. My name is Josh Ocana, and I am currently an undergraduate here at Loyola Marymount University. Therefore, this defensive instruction is somewhat limited to my experience of EDES 488 and the 3-day lesson we had to conduct individually. So, before getting started, a little background on the class that I taught for said 3 days. I taught at Culver City High School, specifically 3 different classes of AP Calculus, AB, for all 3 days. My teacher just thought it might be a good practice for me, and because he also wanted all of his classes to be exposed equally to the new material, whether that's a good thing or not. Since these periods were not my own students, I have nothing but a crude estimation of demographics, but I'd say the classes were about 40% male and 60% female. Furthermore, I'd say in average each class was split into about 40% white, 15% African Americans, 20% Latino or Latina, and 20% Asian, and about 5% other. Again, really rough estimations and really general classifications. So now, the unit we were on was derivatives. Students had previously talked about limits, continuity, and differentiation in the previous unit. By the time I did my lesson, all my teacher's classes were near the end of the unit, so students had already a pretty good understanding of what a derivative is and could compute most of them. The next unit that we'll cover is further applications of differentiation, like optimization and curve sketching. So back when I taught them, the students were barely learning the new skills for the big game. The lesson I taught was on trigonometric derivatives, which aligned to the learning target 2B that I assigned or summed up to be students are able to differentiate a function using different rules/shortcuts based on the function structure. So, in other words, I was teaching students another way of looking at derivatives, specifically for objects that don't move in a nice linear pattern, but rather oscillate. As you can see from this slide, the lesson was centered around showing students, like I said, other functions that they can work with. However, it all had to start with the understanding of why, for instance, the derivative of sine is cosine, based on the definition. I structured my academic goals as if I was teaching the whole unit, so my academic goals are, number 1, that students get to the point that they can solve, or at least attempt, a DOK3 question before the unit test. So my general goal is for all students to be comfortable with DOK2 level questions, including English learners and special needs students. So in the future, I want my students to be able to and want to challenge themselves so they see the applications. The second academic goal is that all students receive a score greater than 1 on each learning target section in the unit test, which would symbolize that all students have at least some idea of how to approach a problem, or to show that at least they tried. As for my first professional goal, excuse me, I want to include at least one hook per new lesson, since I claim that hooks will aid students retain at least part of the concept, or an easy way to remember them. According to a 2004 study by Usha Goswami, I apologize for mispronunciation, quote, analogies at all ages provide logical tool for explaining and learning about the world, contributing to the acquisition and reconstructing of knowledge, end quote. Another study by Anderson, Valero, and Meany showed that how among many high schoolers the word boring was most commonly used to describe mathematics. But once, quote, mathematical content was related to social topics, new descriptors such as meaningful and useful were used to describe math, end quote. For the second professional goal, I intended to have justify, think, partner, share, compare activities on at least 75% of lessons. The reason is that, as supported by Rongjin Huang's research, again, my apologies for mispronunciation, according to his research, sharing one's thinking and results strengthens students' critical thinking skills as they try to formulate a valid argument for why they think their work is correct. Sometimes it actually exposes errors and misconceptions as thoughts are shared. Furthermore, a research conducted by Boaler and Sengupta Irving had struggling students grouped together to go through some problems, and once they arrived to an answer, sometimes with a little guidance from the teacher, the students realized that it was their intellect and their hard work that in the end got the answer, and thus encouraged students to engage more. After the lecture on my first day, students were asked to write about what they liked about the lesson and what they wished I had explained in more detail. As you can see, about 16 of the 64 students that I taught made a point of saying that they really liked the funny ways that I helped them to remember certain properties, such as how sine of a plus b had the same sign as opposed to cosine a plus b, which had the opposite sign, plus or minus or plus b. I am convinced, therefore, that if these many students were sure to point out its usefulness, then surely others must have at least appreciated the trick, or might have been beneficial. So I'll make sure to try to include those in the future lessons. At the same time, a number of students wished that I had given some sort of visuals to show the concept of trigonometric derivatives and their importance. Mostly this extends from the lack of hook in my lesson, since I ran out of time. Thus, it was one thing to see that sine prime of x was equal to cosine of x, but to see a graphical relation might have been a lot more beneficial for the students. Excuse me. Or how it might apply in real life, such as predicting the position of a double-ended punching bag and how its motion changes suddenly when it's hit, or how representations of sound waves are represented with sinusoids, how those analogies might have helped understand the importance of the topic and might have increased the interest. So, for future references, I made sure to make those adjustments. Moreover, I had students write that they wished for a few more guided examples, so for future lessons I plan to split the class into two groups: those who want to try problems on their own while I work, and those that I work with who want or need that extra help or extra problems. In other words, thanks to the feedback, I am now aware that students will many times need that extra help, so I should plan for that. What was great about active practice is that it also allowed me to see an advanced student at work. It may be a little hard to see, but this student was actually evaluating limits using L'Hopital's rule, and therefore the chain rule, which the class hadn't learned yet from either me or their actual teacher. So this particular student even went ahead and taught a fellow classmate, I believe she was also advanced, about the chain rule, which I found really interesting and really kind of sweet. However, I did want him to think further and to not use shortcuts, so I asked him to compute the limit without taking the derivatives. Thus, it became a problem with knowing how to strategically multiply by 1 and add 0 to, in the end, use properties the class had already learned, such as how the limit as x goes to 0 of sine of x over x is equal to 1. It was also great to see that this student also challenged fellow advanced students in the end by making up a random problem, and then the whole group tried to solve it. Although you could see it got ugly pretty quick, the group effort and the encouragement was definitely there. As for my next steps, number 1, a student goal I want them to accomplish or achieve is that the students can tackle a DOK 2 level question immediately after the lesson. That way, if DOK 2 is a starting point, then they will reach a DOK 3 level problem in no time, as was the academic goal, at least before the unit test. The way I will try to achieve this is by having, like I mentioned before, at grade level and advanced students work as a group in trying to solve DOK 2 questions immediately after a lesson, while I take the time to provide guided example for ELs, SNs, and at-risk students. That way, come active practice, these students will be able to tackle a DOK 2 problem as a group, hopefully, and maybe reach a DOK 3 question at least by the end of the unit, depending on their level by the end. By the same research as before, Huang's work showed how a group work helps the development of critical thinking and grasp of a concept as they forge support for their work and analyze it. And that goes for all students, not just the advanced or the at grade level. The second student goal would be that students possess and update a unit mind map that they update after every lesson. Excuse me. This way, students will have to reread their notes and will have to critically think, perhaps with one another, about what were the most important or useful things that we covered that day, and therefore will add to the unit mind map to study in the end. As talked about by Movac and Kanya's research entitled The Theory of Underlying Concept Maps and How to Construct and Use Them. So in the end, concept maps can be really beneficial, but it's up to the students to make sure they keep up with the mind map. Thank you all so much for watching. This has been my defensive instruction, and hope you have a great time. Peace.